All right, guys, good morning. I hope you got the message that I wasn't going to be down today. So I just want to spend maybe about 15, 20 minutes talking about the last two steps, step 4 and 5, that we're going to do for one sample test of a hypothesis, and then go through an example. And it's going to be a little hard to comprehend this way, but this is the only way I can think of doing it on the computer without having a board in front of me. So we'll go through the last two steps here. I'll do an example. I'll put a problem for you to try in the coursework, which you could bring to class tomorrow. And even if even if the concepts we covered today are a little fuzzy, even if you're not 100% sure, is it a one-tail test? Is it a two-tail test? Give the problem a try, because then when you come to class, you'll have more questions about the procedure itself. And I'll give you like 10 points for watching the video and doing the problem. So we're in this lesson. What we're going to do is we're going to go step 4 and 5, which is formulate a decision rule, and then step 5 is take a sample and arrive at a decision. So step 5 is really going to be our computing, like we've been doing for the last 3 or 4 weeks. We're gonna based on step 3, identify the test statistic. We're gonna do a Z or a T. That's what we're gonna choose, and then we need to formulate a decision rule. So really, what we've been doing over the last few weeks, it's going to be we're going to need to do it twice in essence. We're going to need to do it to formulate a decision rule, kind of a go, no go, accept, reject type thing. And then based on our significance level, which was our confidence level, right? We're going to decide whether or not we accept or reject something. So let's kind of go through that. I'm going to skip forward a couple slides here because this is what we covered yesterday. So in step 3, we said we're going to develop we're going to find out what we're going to use, and we've been using up to this point Z's and T's are what we've been focused on. We're not going to be looking too much at this. The chi-squared is a non-parametric test. We don't get to it in this class. I'm pretty sure we don't even get to the F value, though we might see it somewhere. But we're probably not going to be here. Really, what we're focused on are these Z's and T scores, right? So we're gonna determine which one we use, and of course, the Z is when we know the standard deviation of the population. The T is when we don't know the standard deviation of the population. Another thing I need to note as we move along here, really reading and understanding what the question is asking is of critical importance. You might have to read the question 3, 4 times to say, okay, is there a population standard deviation? What is the significance level that it's telling me to use? Is it a one-tail or a two-tail test? So there's a lot of information that you're going to have to glean from the questions that are being asked. So you can't just read the question and say, oh, well, let me just, you really have to take your time and go through it. Because you're going to need what is called a critical value. And a critical value is the dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. So you're going to see as we draw out our normal distribution, we're going to have a point or an area where we say, all right, this is anything beyond this is where we reject the null hypothesis. And then we do our calculation of the critical value and we see where that critical value falls. So those two markings, lines, whatever you want to say on the normal distribution curve is going to tell us whether to accept or to reject the null hypothesis. And that'll be a little easier when we go through this a little bit. So one of the first things you're going to need to determine is whether it's a one-tail test or a two-tail test. And if you look over here, these are both one-tail tests. These are the tails of the distribution curve, right? And you could be looking for something out here, or you could be looking for something out here. It's just dependent upon the way the question is worded. For example, the packaging department at General Foods Corporation is concerned that some boxes of grape nuts are significantly overweight. Okay, so now they're looking at, something that's overweight, something that's greater than what it should be, right? Something greater than. So they're looking down here. This is a one-tail test. is the weight of the cereal boxes greater than what we're accepting or what's acceptable based on our, based on our probability? Okay, is it greater than? If they said they're concerned that some of the grape nut boxes are less than, or they're underweight, then we would be looking over here. Another example might be when we did the tire thing. The mean life of tires, they're concerned that the mean life of the tires is significantly below 60,000 miles. Then we're looking out at this part of the tail. Is it less than what we designate as a critical value? So you might see greater than, you might see overweight, you might see more than, less than, underweight. Things like that are going to be out here in this tail. So read the question. It could be a one tail or two tail. The other thing is it could be a two tail test, and that in that way you're saying we want to see if the weight is significantly different than, right? So if we have a cereal box and we say, look, we're not sure, something's going on in our process. We want to know if the weight is different than, if the weight is not equal to what we say it is. We don't know if it's greater than or less than. We don't know if it's overweight or underweight. We just want to see if there's a difference. And if that's the case, then you're looking at a two-tail test, right? A two-tail test. So if the value falls in here or in here, then we have a problem. If it falls anywhere in here, then we know that we're within the acceptable range. Okay, so just try to digest that for a second. Because that's what in essence, that's what we're trying to do. We're saying, look, we think the weight of the cereal box is, say, 400 grams. Okay, we say the weight is, our average weight is 400 grams. We want to know if it's significantly more or significantly less than that, or in very simple terms, if it's not equal to that. So we do a test, we get 401.3, it ends up being here. We say, okay, it's not out here, it's here. So we're still within the acceptable range. The difference we're seeing is just from the sample that we took. Okay, if it's 399.4, it's here. Okay, it's still within this acceptable range here. And that just because we took a sample, we're going to have a little bit of error, it's acceptable. If we get something here, maybe we get 391 and it's out here somewhere, then we say, no, now there's a problem, now we need to shut the machine down. If we get 403.6 or something out here, I'm making these numbers up, by the way. I don't know if they're going to be significant or not, but it seems like it's far enough from the mean. If we get something out here, then we also reject. So when you read the question, try to determine, is it a one-tail test or is it a two-tail test? Okay, the example that we're going to use today, I believe, is a two-tail test. So just kind of watch the way that that's worded. And, what do you use more, one tail or two tail? I've seen my share of both. Probably I've seen more two tail tests because you just want to see if it is different. If the mean of the population is different than what you're getting. So we talked in class yesterday about some potential products, and we talked, projects for your final projects, and we said, okay, the distance that commuter students travel to school, we don't know. We're not going to go in with a hypothesis that, Central Penn students travel more, so it's going to be a one-tail test. Do they travel more than, right? We really don't know. So we're going to say, if the national average is, say, 20 miles, we're going to say, is it different? Is the Central Penn student, the distance they travel, is it different? Meaning, is it greater than or is it less than? We don't know. We just want to see. So that would be a two-tail test. We may find Central Penn students here. We may find them here. We may find them in the region where they're right on par with the national average. Okay, if we say we want to see we just want to see if Central Penn students travel more than, or if the distance they travel is greater than, then we're just going to do a one-tail test. But for something like that, I would assume you do a two-tail test because you just don't know. So here's our sample for today. And like I said, I'll put another sample in there. Please try it. It's worth 10 points. Bring it to class, and we'll go over that one, and we'll go over a couple more because this might take a little while to kind of get it vet it out. So Jamestown Steel Company manufactures and assembles desks and other office equipment. The weekly production of the blah, 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 blah desk follows a normal probability distribution with a mean of 200 and a standard deviation of 16. Okay, so what am I doing here? As I'm reading this, I'm saying this company manufactures desk and other equipment. They have a lot of data. They have years and years and years of data. They know that the population mean is 200 and the population standard deviation is 16. It doesn't say population standard deviation, but the weekly production of this follows a normal probability distribution with a mean of 200 and a standard deviation of 16. So I know that data is coming from mounds of data that they compiled. It's population data. Right there, I know I'm doing whatever I'm doing a z-test. That's going to be my test statistic, is going to be a z, because I know the population standard deviation. Recently, new production methods have been introduced and new employees hired. The vice president would like to investigate whether there has been a change in production. Notice how he says, wonders if there's been a change. So that's an important consideration there, because he didn't say he wants to see if production has increased. He didn't say that. He said he wants to see if there's a change. So there's a potential that going into this experiment that he's going to run, they could be producing less tests. Maybe these production changes weren't very good and they're producing less than 200. He doesn't know. He doesn't know that it's going to be more. So he just says, I want to see if there is a change from that 200 number, right? He didn't say greater than, he doesn't say less than. He says, I just want to see if there's a change. That tells us it's a two-tail test. Okay, this here tells us we're looking at a two-tail test. A sample from last week's weekly production yielded a mean of 203 deaths. So again, before we even take a sample, we kind of say what we want to do. We want to see if there's a change. We know it's a two-tail test. We know there's population standard deviation. We're doing a Z. We take a sample. It ends up being 203.5. Okay, it ends up being 203.5. That's the X bar that we're going to use. And he says, look, I want to be really sure about this. I want to use a significant level of 0.01. So, that's a 99% confidence, right? I want to test this at a 0.01 significance level because it's that important, and the results are that critical. So the thing this doesn't tell you, by the way, and it took me a little while to figure this out, the sample size is 50. So for some reason, it doesn't tell you in the problem what the sample size is, but they took a sample size of 50 desks. So from that sample of 50, they got a 203.5. We want to see, is that different from the 200? You might be saying to yourself, sure, it's different. It's 203.5, it's more. But is that difference caused by our sampling error? Or is that because of the changes that we made in production and the new people we hired? Okay, that's ultimately what we're deciding. We can't take every desk coming off the line for the next 7 months and see if it's different. We have to take a sample. We take a sample of 50. It's 203.5. Is that enough to lead us to believe that these new production methods and people are causing this change in production? We know it's an increase, but we went into this saying, is there a change? So first step is we state the null hypothesis. We say the population standard deviation is equal to 200. The alternative, it is not equal to 200. So again, if I was to put that into words, I would say there is no difference. There is no change in the population standard deviation from 200, or in the population mean. There's no change in the population mean. That would be my null hypothesis. Remember, there's a no or a not. There is no difference. The population mean is a 200. The alternative is it's not 200. It's either way less or way more. The significance level was stated in the problem, 0.01, and we know it's going to be a z because the population standard deviation is known. So the first 3 steps are relatively easy, right? And we went through those yesterday. We know it's going to be a z, so there's our formula for a z, right? We've been doing that 1,000 times now. The sample mean minus the population mean, standard deviation of the population divided by the sample size, which we know is 50. And I put this down here for you so you would see what it looks like. And we get a z-score of 1.547, okay? 1.547. That's going to be a very important number. Okay, so just keep that number in mind as we move along. We figure out what the z is of this problem that we just did, okay? We figure out the z, and it's 1.547. Now, in the past, we were using that to determine probability and the area under the curve. We're not going to do that right now. What we're going to do is we're going to see if that is within the range that is acceptable to us based on that significance level that we chose, okay? So let's look at this. This is why I keep saying it's so important to draw these things out and have these things mapped out. If you, let me just see something real quick. Yes. So this is, if you look at the previous screen, this is the 1.547 that we got. Okay. This is the 1.5. But before we would even do that or put that in, we would have these critical regions already identified. Okay. We would have these critical values already identified and marked on our normal distribution. Okay, so this minus 2.576 plus 2.576 come from that significance level that we identified. Okay, the 0.01, the 0.01 significance level. Okay, that's where the number 2.576 comes from. And if we go to our z, which is what we're using, right? We're using our z values for 1% significance. The region that we're looking at is 99%, right? So 0.495, 0.495. Is that right? 0.495, 0.495 should give us 99%. Okay. And if you look over here, you could obviously use either one of these. Really the answer is somewhere in between. But if we use 0.495, again, this area here is 0.495, this area here is 0.495. And what does that translate to? It translates to a 2.58. I think it's a 2.57 on the other one, didn't it? Yeah, 2.576. Okay, so they split the difference. So they actually use the number in between here. So 2.57576, somewhere in between here is the number that we're using where we got that critical values from. So we put that there and we say, okay, anything over here in this blue region means that there's a difference. There's a difference. It's not, the mean is not, the population mean is not 200. If it's out here in the blue region, it is something different. In this case, we know it's over here, so it would be more than what our critical reject area is. If it's down here, we know it would have been in our reject region. So we do this first. So we have our bell curve. We put our critical numbers there. In this case, based on our z values, it could also be a t, but based on our z values, they're out here. Then we went ahead and we calculated what the z is based on the information that was provided, based on the sample of 50 that we took, and we got this 1.547. Remember, 1.547. 1.547 is less than 2.576. So it's somewhere here. It's, a full deviation down this way. So it's because it's less than this reject area, this reject line, we do not reject the null hypothesis. We accept the null hypothesis that there is no difference. Right? So out here is where we would reject the null hypothesis that there is no difference. Here, we accept the null hypothesis. Okay? So 1.55 falls within the do not reject the null hypothesis region. H sub O is not rejected. We conclude that the population mean is not different than 200. Okay. So in the last 1 minute, let me explain what that means. So what we're saying is from our sample, we got 203.5. The vice president wants to know, is all this equipment, all these employees, is it making a difference in the population mean? Is it more than what we've been doing? The answer is no. The answer is no. The answer is we could pull another sample of 50 and easily get a 197.5 or 196.5. So from that, you would conclude that the new equipment, the new machine, the new people, they're not causing a significant difference in the amount of desks and other office equipment that's being produced. Okay? So The difference that we see there, that 3.5 difference, is just a result of the sample that we're taking. Okay, so that's very important stuff. That's a very it's a very involved kind of explanation of the last two steps there. But like I said, I'm going to post something in the course room. Please give it a try. Please bring it to class tomorrow. Bring questions. I think that'll help us get through this a little quicker, and then we'll go through a couple more in class, and then we'll practice some of this also next week, because you might be using something similar to this, or very similar to this in your project. So again, I'll see you tomorrow, and bring your problems and your questions to class.